Section 7.1, Integration by Parts. In Chapter 7, we want to turn our attention away from applications of integration and look at new techniques of integration so that we're able to calculate a wider class of integrals, both definite and indefinite. The first of these is the technique called integration by parts, which is the integration analog to the product rule. So to show where integration of parts comes from, let's first look at the product rule. So suppose we have two functions, u of x and v of x, and we're looking at their product, and we want to take the derivative of that product. Well, by the product rule, we get derivative of the first times the second, plus the first times the derivative of the second. If we take this line then and anti-differentiate both sides with respect to x, then this side, we would just get the antiderivative of this quantity prime, which is just going to give us u of x times v of x. And on the other side, if we rewrite this in Leibniz notation, u prime of x as du dx, we leave the v of x alone, we distribute the dx, so we split this into two integrals. Then we'll have the integral of du dx times v of x times dx, plus the integral of u of x times dv dx times dx. Now, just operating formally, even though these aren't fractions, if we operate formally and treat them as they are, then you can think of these dx's as canceling. This is just a heuristic. And here we would have a uv on the left-hand side, and on the right-hand side we'd have an integral of a v du plus an integral of a u dv. If we take this and rearrange this and solve for u dv, then we get the so-called integration by parts formula that says the integral of u dv is uv minus the integral of v du. Notice we got this by just solving for this term and throwing this to the other side. This is called the integration by parts formula, and we just want to use this to tackle. It can be a useful tool for tackling certain types of products, ones that fall into the template. Let me show you what I mean by falling into the template here. Let's look at the example, the integral of x sine x dx. And if you pause for a moment and look at this, if you were just confronted with this integral, you might be tempted to use a u substitution. But try as you might, a u substitution is not going to help here. But this is a product, and we're learning the new technique of integration by parts, so we want to try to do that. Here it's going to feel sort of like a substitution, but instead of picking a u, you're going to have two components to pick. You're going to pick a u and a dv, and then from that, you're going to calculate du and you're going to calculate v. Let me show you what I mean in practice. We're going to pick one of these to be our u and one of these to be our dv. Well, since dv is a differential, it needs to contain the differential always. So since we don't have any experience, we'll just pick this to be u. We'll pick this entire thing to be dv. So I'll take my u to be x, my dv to be sine x dx. It is important that the dx is in there. And now once we've selected this, we'll just take the derivative to calculate the differential du. So you can think of if you've picked your u to be x, then you would calculate du dx to be 1. And then if you multiply both sides of that by dx, you would get du equals 1 times dx. On the other hand, if you've picked your dv to be sine x dx, if you anti-differentiate both sides of this to recover v from its differential dv, then you're anti-differentiating this, and so now you get a minus cosine x. And this is where it feels a little bit different than regular u substitution. On one level, you're picking two things instead of one, and then on another level, you're calculating this, which feels like u substitution, by taking a derivative, but you also have to calculate this not by taking a derivative, but by calculating an antiderivative. Let's see if this helps. So if we put this into our integration by parts template, then we'll have, starting at this integral, we know that this integral, u dv, which we've declared those choices, is equal to u v, which we've calculated, minus integral v du. And so now we take inventory and we see if what we turned this integral into is something that's more easily and more readily doable than the integral that we started with. Well, here there's no integration to do, so we'll just simplify. Here we'll just pull the minus out and we'll take inventory. This is what it is. This becomes a plus integral of cosine x dx, and the question is this integral doable? And yes, it absolutely is. It's in our standard repertoire, and so we'll anti-differentiate the cosine x to get sine x. We'll pick up a plus c, our constant of integration, and what we've concluded is that the integral of x sine x dx is negative x cosine x plus sine x plus an arbitrary constant. And just to check this, we can always check if this really is the antiderivative for this function, then we should be able to take the derivative of this function and get this as the answer. So let's just check that. The derivative of this function, by linearity, we just take the derivative of the pieces. To take the derivative of this piece, we use the product rule. Derivative of the first times the second plus the first times the derivative of the second, then plus the derivative here, and then plus the derivative here. When the calculus dust settles, you can see that we get x sine x, which is exactly what the integrand was here, and so we conclude that indeed this is an antiderivative for this function. Okay? Let's look at another example. If we have the integral of x ln of x dx, now I know that I've already declared my choices here, but it's very helpful to pause for a second, look at the blue integral, and just see what might you be tempted to choose for your u and your dv. Here I'm going to pick my u to be x. I'm going to pick my dv not to be ln of x, but it needs to be ln of x times dx. ln of x dx. Once I've made those choices, I'm going to calculate du. So du dx would be 1, so du is dx. Here I'm going to anti-differentiate, and that's why it's important that you pick up the differential here. If you're going to anti-differentiate both sides of this, then you need the differential here. So now when I anti-differentiate dv, I get v. When I anti-differentiate the ln of x dx, that's not in my standard repertoire. So I don't know how to calculate that antiderivative right now. And this is what it feels like sometimes when we make a choice, and then we look at the consequences of that choice, and we see, are we going to be able to make it work? And so on one level, we have to be able to compute the du and the dv, and here we kind of get stuck. What is that antiderivative? So this just says sometimes we have to be judicious in our choices for u and dv. We don't want to be on autopilot and always just take u to be the first thing and dv to be the second thing. Sometimes you need to switch this order. And so here, we're going to think of this x ln of x. We're going to rewrite it as ln of x times x. And then we'll try our u here to be ln of x. We'll try our dv to be x dx. And when we do that, du dx here would be 1 over x. So du is 1 over x dx. dv is x dx. So anti-differentiating both sides, v is x squared over 2. And now if we put this into our integration by parts template, then we would get here the integral of u dv should be uv minus integral v du. And now the moment of truth, there's nothing to do here. It is what it is. So what we're really doing is seeing how doable is this integral. Is this going to be something that's readily solvable? So we'll simplify this. We'll pull the 1/2 out. The 1 factor of x will cancel, and we get the integral of x dx. This is a very doable integral, so this is very reassuring. We'll just leave this alone. We'll leave the minus 1/2. We'll use the power rule here. We'll pick up our constant of integration, and we've just found the antiderivative for our original function, x ln of x. So a little rule of thumb here is when you're picking your u and your dv, since you know that whatever you pick for your u, you're going to differentiate it, and whatever you pick for your dv, you're going to anti-differentiate it, then one rule of thumb is, in general, you should pick a u that's going to be easy to differentiate, and you should pick a dv that's going to be easy to anti-differentiate or integrate. And so don't just fall into the trap of always picking this to be your u and this to be your dv. Sometimes that'll work. A lot of times it'll work. But really, you'll be able to feel when it doesn't work when you hit an integral that's not doable, or you hit a du that's starting to get messier and messier. And this you'll learn more through experience with examples. Okay. Sometimes you might have to use integration by parts more than one time. Let's look at this integral. If you have the antiderivative of x squared e to the x dx, here, going by the rule of thumb that I just outlined, we want to pick our u to be easy to differentiate and our dv to be easy to integrate. Well, it turns out that both of these are easy to differentiate, and both of these are easy to anti-differentiate. But one thing I notice is this function gets simpler when I differentiate it, and it gets more complicated when I anti-differentiate it. Of course, e to the x, its derivative is e to the x, its antiderivative is e to the x. So really it doesn't matter whether you differentiate or integrate this one, but it feels like I should use this to be my u. so that I'll get something simpler when I differentiate. And we'll just see if we can get away with it. We'll try that. If it doesn't work, we'll come back and make another choice. So if we pick u to be x squared, then our du dx would be 2x. So our du is 2x dx. Our dv then will be e to the x dx. So anti-differentiating this, v would be e to the x. Let's pop this into our template. We get that the integral of u dv is uv minus integral v du. This is what it is. And here we're just going to see how doable is this integral. Well, we'll factor out the 2. We'll rewrite this as the integral of x e to the x. And if we look at this, that integral we may have some pause on. A u substitution is not going to work. But it turns out that if we perform another integration by parts just on this integral, then we'll be able to finish this integral out. So here, we'll do parts again on this little piece. And we'll pick u to be x. Then du will be dx. dv will be e to the x dx. Your v will be e to the x. When we put just this integral, we'll go off to the side and just do this integral. We get uv minus integral v du. This is what it is. This is a straightforward integration, so we just get e to the x. Notice I don't have to pick up the plus c because I know that I'm going to put a plus c at the very end of the overall integration, so I don't need to keep track of that along the way. That's why I didn't do it here, and that's why I'm not doing it here. So that means if we just copy this back down, we still have the minus 2, and now this integral we just did here. We'll paste this in right here and pick up our constant of integration. We could distribute this too. Those are really just cosmetics, but we'll distribute that, and now this is the antiderivative of the original function that we started with. So sometimes you may need to use integration by parts more than one time. With experience, you'll develop a feel for this. If this started getting messier and messier, it might make me rethink my decisions. But it turns out that one integration by parts, notice it knocked this power, this x squared, down to an x to the first power. And now one more integration by parts got rid of the power of x altogether and made this doable. Now sometimes it may seem like if you follow that advice that you're sort of chasing your tail. Look at this example. If you look at the integral of e to the x cosine x, and these types of integrals come up quite a bit in applications where you have an exponential times a sine or a cosine. So this is a very common type of integral that we'll need to compute. And so here, e to the x is both easy to differentiate and anti-differentiate. Cosine x is easy to differentiate and easy to anti-differentiate. So I really don't know whether picking my u to be e to the x or picking my u to be cosine x will be better. So we'll just make a move and we'll see what happens. I'll just pick my u to be e to the x, my dv to be cosine x dx. Calculating my du dx would be e to the x, so du is e to the x dx. Anti-differentiating cosine x, I get sine x. I'll put this into the template for integration by parts. I get uv minus integral v du. Leave this alone. I'll rearrange this because that looks like a product. A regular u substitution isn't going to work. I'll try parts again based on the last example. I'll pick my u to be e to the x, my dv to be sine x dx. My du then is e to the x dx. My v is negative cosine x. And if I do just this integral, not with the minus, but just the integral of e to the x sine x then would be uv minus integral v du. This is what it is, so we leave it alone. When we do this integral, we ask how doable is that? Well, that integral doesn't seem to be very doable because it's the same integral that we started with. So it feels like we're sort of chasing our tail. We're following integration by parts, and it seems like we're just getting right back. We're not getting a resolvable integral. We're getting right back to where we started. But this is actually something that can happen, and we want to be prepared for it in integration by parts. And so what I want to do here is just live with the calculation that I've got. So I'll paste in this answer for the antiderivative. I know it has an unresolved integral in it, but let's just paste this in for this, remembering that there's a minus in front of everything, so those parentheses are very important. And let's just assess the situation. What we've concluded is that the integral of e to the x cosine x dx is equal to this stuff. And so if I distribute the minus, that means the integral that I seek is equal to this. And now I notice that this integral and this are the same, and that's the creature that I'm looking for. So why don't we just throw this to the other side, and we'll get when we have this, if I throw this term to the other side, then I'll have 2 copies of e to the x cosine x equals this. And then if I just divide through by 2, then I get the integral that I seek is 1/2 times this stuff, plus I'll pick up the arbitrary constant of integration. And I refer to these as integrate by parts twice and solve for the integral. So notice what we had to do. We started here, we integrated by parts once, we had to integrate by parts again. When we did that, what we got in this unresolved integral is the same as what we started with, which looks like it's a lost cause, but actually it's very nice, because if I just write down this integral in terms of this and throw that to the other side, I'll pick up 2 copies of the integral that I seek, and I'm able to solve for the integral that I'm looking for. This is a constant thing that happens when you have exponentials times sines or exponentials times cosines, so be on the lookout for it. Now, what about definite integrals? When you have definite integrals by parts, you do not change the limits of integration. And so this feels a little bit different than u substitution, and it's because we're not really making an overall substitution, we're making more of a template change. And so here, if we take our integration by parts formula, one of the little different things is, if this is a definite integral, the integral from a to b of u dv, then this is going to be uv evaluated from a to b minus the integral from a to b of v du. So you do need to evaluate this between a and b. Let's look at this in practice. If you have the integral from 1 to 2 of ln of x dx, then I'll pick my u to be ln of x. I'll pick my dv to be dx, which you can pick your dv just to be dx. I will calculate my du. Here my du dx would be 1 over x. So my du is 1 over x dx. I'll anti-differentiate. Remember, there's an understood 1 there. If I anti-differentiate this, here I get a v. The understood 1, I pick up an x. The limits, I'm just going to leave them alone. And so this says that the integral of u dv is uv minus integral of v du. But this time, we have to evaluate this from 1 to 2, and this integral is an integral from 1 to 2. And one of the reasons to remember not to change the limits of integration, notice we never do really put a u and a v. This is an x integral, and this stays as an x integral. Just look at the blue. Everything stays in the x variable, and that's why our limits stay in the x variable. That's in contrast with a regular u substitution, where, for example, we start with an x integral, but then when we make the u substitution, we transform it into a new variable integral, a new u integral. And in that case, we needed to change our limits of integration. Here we're just basically using the u dv, du, and v paradigm to help us line up the parts in the blue integral to use the template. That's a way to remember not to change the limits in a definite integration by parts. So when we do this, we just have x ln of x evaluated from 1 to 2 minus, notice these x's cancel. I get the integral from 1 to 2 of 1 dx. Here, this is just 2 ln of 2 minus 1 ln of 1 minus, this is anti-differentiate, you just get x evaluated from 1 to 2. Here, this is what it is. The ln of 1 is 0. The parentheses are very important here. You're subtracting this entire term, so those parentheses are important. And I'm evaluating the x at 2, evaluating the x at 1, and subtracting. Those parentheses very important. When the algebra dust settles, we get 2 ln of 2 minus 1. And always keep in mind what the interpretation of this integral is. It says if you were to graph y equals ln of x, you will look at the area under the curve from 1 to 2, that the exact area under the curve is this value, 2 ln of 2 minus 1. Finally, sometimes parts and u substitution need to be used in tandem. So remember, whenever we learn a new technique of integration, it can always be rolled together with any other techniques of integration that we use. It's just another tool in our toolbox. So for example, if you had the integral of x cubed e to the x squared dx, you might be tempted to use parts here. Okay, it's a reasonable move. If you pick u to be x cubed, then my dv is going to be e to the x squared dx, but how am I going to anti-differentiate that? If you pause for a moment and think about that, that's a complicated integral that I'm not sure at all how to do. So that gives me some pause, and you might say, oh, well, maybe I need to swap the order of these. So I'll pick my u to be e to the x squared, and I'll pick my dv to be x cubed dx. Okay, that seems more reasonable. But if you look at this, when I calculate the du is getting very complicated, which doesn't mean it's wrong, but it does give me some pause. When I calculate the dv, this is okay, but it is looking quite messy. I'd probably have to push this a little bit further, or you would probably have to push this a little bit further to actually write it out and assess whether the integration by parts formula is going to get us home here. But let me offer you an alternative, and I do encourage you to do that on your own. Just write that out and kind of see what it looks like. But here I'm just going to restart by using a substitution first. Now I've already used the letters u and v, so I don't want to use those letters. How about I'll just go down the alphabet. I'll let w be x squared, so I'm looking at this integral. I'll let w be x squared, since it's the e to the x squared that was causing me some pause. Then dw dx would be 2x, so dw would be 2x dx. And if I look at this, if I'm using this to be my w, then I'm looking at, if I write the x cubed as x squared times x, then I know the x squared will be a copy of w, and I'll have an x dx left over. So why don't I solve for those leftovers and say, well, let's isolate the x dx, and I'll get 1/2 du. Well, if I do that, then this integral, if I split the x cubed into an x and an x squared, I've already determined that I'm going to let this be w, so this will be w. I've said that x dx is going to be my 1/2 du. Then now if you look at this integral, it becomes a 1/2 w e to the w dw. Now if you just blur your eyes for a moment and don't think about the letters, this is an integral of an x e to the x dx. This is a doable integration by parts. Matter of fact, we did it up above just a few moments ago. We had an x e to the x integral right here. So we saw how that integration goes. We just happen to have the w letter instead of the x letter, but we know that this game plan is going to work for us. So if I go back down here and I look at the result of my u substitution, of my w substitution, this is a doable integral by parts. I will go through the motions here, and we'll say, well, I'll let my u be w. My du dw would be 1, so du would be dw. dv then needs to be e to the w dw. So dv, if I anti-differentiate that, I get e to the w. And now let me just follow the integration by parts template. Now remember, this 1/2 is out front, and it's multiplying everything. So it's multiplying all of this. So these brackets are very important. And I'll get u v minus integral v du. When I do that, there's nothing to do here. We look at this integral. Is that integral doable? Sure, it's doable. The integral of e to the w is just e to the w. I'll pick up my plus c. Now I can't stop here. Since I started in the x variable, it only makes sense that I would stop in the x variable. So this is where the doing this in tandem with a substitution comes into play, and I need to translate this back to the x variable. But remember, w was x squared. So I'll just come down here, and where I had a w, I'll put an x squared. Where I had a w, I'll put an x squared, put an x squared. And now this is the antiderivative of the original function that we started with. So the key idea here is when you learn a new technique of integration, it doesn't render the other techniques useless. And you actually need to be ready to mix and match the different techniques of integration, and this will come with practice.